Hey guys, welcome back. In this section, we're going to look at 11.5 on the Bohr model of the atom. The picture you're looking at right here shows us the progression of models of the atom that physicists and chemists developed over a period of, golly, it wasn't real long, maybe 30 years or so, 35 years. We start over here, the very end of the 19th century, about 1897 or so, with the J.J. Thomson cookie dough model or plum pudding model of the atom. J.J. Thomson recognized that atoms were made up of positive and negative pieces and that the negative pieces could be pulled off. About, I don't know, 12, 13 years later, Ernest Rutherford put together the gold foil experiment. And what he recognized is that all the mass and positive charge of an atom is concentrated in a tiny, tiny nucleus, and that the electrons are occupying a cloud that has almost no mass surrounding that. The scale here, of course, is wrong. The nucleus is about 100,000 times smaller than the electron cloud. Go forward in time, not too much further, really just a few more years, and we've got this model of the atom, the Bohr planetary model of the atom, in which the electrons sit on energy levels or rings that go around the nucleus. And he even said how many electrons you could put on each ring, and we'll come back to that later on. And then finally, go forward in time, maybe a couple more decades, and we've got the wave model, or sometimes it's called the wave mechanical model of the atom, where we talk about things like orbitals and so on. We'll get into that later in the chapter. So here are the two people credited with coming up with this planetary model. Bohr gets his name on it. I'm not sure why Rutherford is ignored, but on the left side you've got Niels Bohr from Denmark, and on the right side you have Ernest Rutherford from New Zealand, and they work together to come up with this planetary model. Now, here's what people believed should have happened. According to the kind of physics that Isaac Newton developed hundreds of years ago, a couple centuries ago, anytime you have an electric charge that is either speeding up, slowing down, or changing direction, right? And going around in a circle is definitely changing direction. It ought to lose energy to light. It ought to radiate away its energy. And because it's losing energy, this spiral should get smaller and smaller, or tighter and tighter. As the electron radiates away its energy, it should get closer and closer to the atomic nucleus until finally, blop, it falls into the nucleus. And when people did calculations of this, it should have happened in human terms almost instantly, right? That's obviously not what happens. The universe is infested with stable atoms where the electrons never fall into the nucleus. In fact, we don't observe this to happen at all. So what's going on, right? There was something wrong with classical physics. This was an early foray into quantum mechanics, not the earliest, but sort of a people understood that something was missing here. Well, here's what Bohr came up with, what Niels Bohr came up with. To fix the problem, he said the nucleus is at the center. Again, not to scale, it'd be much, much smaller on the scale. And then these electrons are going to occupy rings, but they have to stay on a ring. They don't fall in or spiral into the nucleus. Why? Well, the reason has to do with something called conservation of angular momentum. Basically, the conservation of spinning. If this If this were correct, we would start with an electron that was spinning, and we would end with no spinning. In other words, spinning would not have been conserved in the universe. Now, if you dig into the details of this, you could quibble a little bit, but basically what that means is this kind of spiraling is not allowed because it removes spinning from the universe, and the conservation of angular momentum doesn't allow that. Or maybe a more correct way to say that is we don't observe the universe to do that. The universe, for whatever reason, seems to really want to conserve spinning. So the electrons stay on these rings and they spin and they spin and they spin. They can move between rings. As you know, to jump up to a larger ring, the electron has to absorb an exact amount of energy, an exact color of light, and to move down, that electron would have to emit an exact color of light. And you can go back to section 4 for all the details on that. There are more energy levels than those shown here. In fact, there are an infinity of energy levels that electrons are free to move around as long as they can get bumped up by absorbing the correct amount of light. Bohr understood this model was wrong from the beginning. He went into it thinking of it as a stepping stone that would lead to a more correct description of atoms. And it was actually pretty good. Bohr's model described the emission spectrum of hydrogen exactly. Using some math that we don't get into, Bohr was able to predict or account for this color of red light that hydrogen emits. And this color of light, and this color, and this color, he was able to account for all those colors by specifying the exact amount of energy in the first ring and the exact amount of energy in the second ring and how much energy would be released by transitioning between the two. And so although we're not getting into the details of it, Bohr's model was really a home run for the hydrogen atom. But that's where it fell apart. Bohr's model didn't work for anything else besides hydrogen. And so here you can see another depiction of Bohr's model with the ground state, an excited state, another excited state. For some reason, putting a second electron in made these predictions not work. And then with lithium, a third electron, beryllium, a fourth electron, and so on and so forth. And so what physicists wanted was a description of atoms that would work for all of the elements and not just hydrogen. And that's what's going to take us into the wave model in the next section.